Assalamu alaikum. My name is Khalid Alnajjar, and I will be your tutor for this session, inshallah, which I will be talking about hemodynamics. The first part, the second part will be taken care of by my colleague Samhar later today, inshallah. So before I start, down here is my name and my email and contact number in case you have any question about this lecture, this block, any other block, or any other question. I'll be more than happy to help. Please do not hesitate to contact me. Like, let me start. These are the learning objectives of today's session. You can read them alone when you're studying the lecture. This slide, the doctor here listed a bunch of equations that you are supposed to memorize, as he wrote over here, down here, that these formulas will not be provided in the exam and you should memorize them. Please don't panic. They are easy. Once you understand them, you will never forget them again, inshallah. I will come back to this slide when I finish, so we can just go over them really quickly. I can't go over them now one by one because you don't know any of them yet. Type. This lecture is basically about hemodynamics. What is hemodynamics? Let me introduce it to hemodynamics before I start. Hemodynamics simply is, I don't want to say the physics because physics sometimes can sound scary to some people. I'm one of them, by the way. But it basically describes how blood flows through vessels and through your whole body systematically and by organ. Okay? Inshallah, this term you will be more familiar with this term by the end of this lecture. The doctor here wants you to know that our circulation, or the circulation in our body, is either in series or in parallel. Okay? What's the difference between these? Basically, the difference is how can you control the circulation right here. This is the difference between series and parallel circulation. From this slide, you just need to know that series circulation, or circulation that is in series, is basically either the systemic circulation or the pulmonary circulation. Yani whenever the left heart pumps the blood that circulates to each organ, this circulation right here is systemic. Or whenever the right heart pumps to the lungs, this circulation right here is systemic. Not the circulation in the lungs, not the circulation in each organ or in each system, but the circulation to the system and to the organ is in series, okay? And what does in series mean? In series basically means that the whole, or the destination of both destinations, or all destinations, will receive the same volume of blood per minute, okay? Per minute. So if we pump, for example, just for the sake of an example, 10 milliliters of blood per minute, this is not a real number, by the way, to the lungs, this should be the case to the whole body, okay? Why? Because both the circulation to the lung and to the rest of the body is in series, okay? Parallel arrangement or parallel circulation is basically the circulation within the organs or within the systems. Clear? Now, the difference here is the parallel circulation when compared to series circulation. Parallel circulation is quite independent. And what would that help us in, or why would this be beneficial? It's basically, when it's independent, you can control and regulate the blood flow to that circulation, which is the parallel circulation, rather than regulating or controlling the whole blood flow, or the whole body's and circulation's blood flow. What do I mean by that? So within each organ or within each system, we have parallel circulation, as I mentioned. So if we are exercising, for example, when you're exercising, you need more blood into your skeletal muscles, but less blood into your gastrointestinal tract, or GI. Okay. So now the body will decrease the blood going into your GI, and will increase the blood going into your skeletal muscles. And this happens because of the parallel circulations within these systems or within these organs, okay? Otherwise, you cannot do this in a series circulation, because if you did this, you will disrupt the whole circulation, because as I said, the same amount of blood is delivered per minute to all destinations. Okay, trying to simplify my terms here as much as possible for you to understand it all. Okay, this is what the doctor needs you to know for now. Okay, now what are the parameters that affect the hemodynamics or more of the blood in the circulation and all its parameters? Type 1 is the blood vessel diameter, so vasodilation, vasoconstriction, mean blood flow velocity, or the speed or the velocity of the blood flowing in these vessels, the cross-sectional area of the vessels, and this is different than the diameter because it's the area of all the vessels or a group and bunch of vessels, the area of these vessels, not the diameter of each vessel separately. Okay, the blood volume distribution, as in how much volume we have going to this system, how much volume we have to that system, or how much volume we have in this vessel, how much volume we have in that vessel, or in the aorta and in the arterioles. Okay, TPR or SVR, total peripheral resistance or systematic vascular resistance, will definitely affect the hemodynamics because the resistance is again limits the blood flow. Mean blood pressure, it's basically the pressure of the blood in the vessels and what affects it. I will go over these one by one now. There's a slide dedicated to each one of them. Okay. Right. Let's start with the vessel diameter. Okay. This sketch right here basically shows you how the diameter changes from a vessel to a vessel. Yani, the diameter in the aorta or in the great vessels is bigger, way bigger than the diameter in the arterioles or the capillaries. And this makes sense because you have your capillaries in the organs, okay, or the arterioles in the organs, and you have the aorta taking the blood directly from the heart. So you need the diameter to be wider, okay? You see here, wide and then narrow and then wider again, because you have, after the capillaries, you have venules, which is the equivalent to arterioles, and then venous branches, greater veins, which is equivalent to the greater arteries, and the vena cava, equivalent to the aorta. So it's kind of going big, small, big, okay? When you look at the velocity, or let me explain something before the velocity. I'll come back to the velocity. طيب. Look at the total cross-sectional area. This is very interesting. You have the aorta here, and then the great vessels here, like the internal carotid, the femoral, the brachial arteries. Those are all great vessels, great arteries, sorry. They have wider diameter than the capillaries and the arterioles and the venules, as I explained before. However, the cross-sectional area is quite the opposite. Why? Because the area of the aorta, for example, or the femoral artery is basically the area of the vessel itself. Okay, but why is the cross-sectional area in the arterioles and the capillaries way bigger than more than the cross-sectional area of the great vessels and the aorta? It's because you have small, very tiny arterioles and capillaries, but too many of them. Okay, so you have too many arterioles, too many capillaries, and each one of them is very tiny with very small diameter. But when you add them all together, they create this huge, vast cross-sectional area. I hope you can appreciate it right here. So, for example, aorta has the cross-sectional area of the aorta is 5 centimeters squared. Okay, but the cross-sectional area of the capillaries is 3,500 centimeters squared. This is huge. This is vast. This is very big. Why? How do we have this huge cross-sectional area in our bodies? This is because tiny vessels, but too many of them creating this cross-sectional area. Okay. And if I'm gonna go back to the velocity right here, interestingly, the velocity, what controls the velocity, the blood flow velocity? It's not the diameter, it's the cross-sectional area. Okay. So you would think that the smaller the diameter is, the more the speed is. But no, it's the opposite. It's completely the opposite. The wider the vessel, the artery or the vessel is, the faster the blood flow in that vessel is. As you can see here, I hope you appreciate how a very wide diameter of the aorta or great vessels has a very high speed, okay, 18 and then 5 and then 1.5 centimeters per second, okay, the velocity. However, when it comes to capillaries, very small diameter and very slow blood flow, okay. Now look at the cross-sectional cross-sectional area. Again, remember, we said that the capillaries has the largest cross-sectional areas among our vessels in our body, صح? Largest cross-sectional area, slowest blood velocity in them, okay? Lowest or smallest cross-sectional area, fastest blood flow velocity. So the relationship here kind of is opposite. So the larger the cross-sectional area is, the slower the blood flow is. The smaller the cross-sectional area is, the faster the velocity is. And I want to remind you again that the diameter is opposite to all of this, okay? So if I want to combine them all together, just not to confuse you, the wider the diameter is, okay, that's one. The wider the diameter is, the smaller the cross-sectional area is, the faster the blood flow velocity. Take an example, the aorta. The aorta has the widest diameter among all the vessels, okay? And widest diameter means the smallest cross-sectional area, صح? Look at it here again. Widest, this is the aorta, has the widest diameter. It also has the smallest cross-sectional area. And the blood flow velocity in the aorta is the fastest, okay? Kind of opposite relationship here, and vice versa to the capillaries. And the same equation applies to the veins, because I told you every group of arteries, arterioles, great arteries has an equivalent with the veins, okay? Last thing here is the blood volume distribution. So how much blood is in this vessel? See this, I would understand the initial thought would be, oh, largest cross-sectional area means largest blood volume distribution. No, this is not the case. Why? Because there are many other factors affecting the blood volume distribution, or the amount of blood the vessel can carry. I'll go over them later, inshallah. But I just want you to know that the veins in our body carry the most blood. Most of our blood in our bodies is in our veins, okay? And if you can see here, the doctor mentioned something very nice here. Okay, it's mentioned in later slides, but he says here it's a reservoir. It's a reservoir of our blood. As I said, most of our blood at rest is maintained in our veins, for a simple interesting reason here, because of the effect of the gravity. Again, when you're standing, because of the effect of the gravity, the blood pools down in your legs, in the veins of your legs, okay? Like TPR. TPR is another parameter that affects the hemodynamics or the blood flow in the body. What is TPR? TPR is resistance. Total peripheral resistance, known as SVR, or systemic vascular resistance. You can see here. You can see here that which set of vessels have the largest resistance. It's the capillaries. Again, why? Because it has the smallest diameter. Okay, the smallest, thinnest diameter, tiny vessels, the capillaries. So they would have more resistance. The smaller the diameter is, the larger the resistance is. Look at the aorta here, or the great vessels. The great vessels are very wide, okay? So they would have less resistance than the arterioles or the capillaries. Arterioles are known to have the largest or the highest resistance among all vessels in the body, okay? Why? Because they are muscular arteries. They are known to be muscular. They have muscle, and yeah, they are small muscular arteries. Hence, they have the greatest change on resistance in the systemic circulatory system. So basically, if you dilate all the arterioles, the blood pressure will decrease. Okay, if you constrict the arterioles, the blood pressure will increase, because they oh no, you know what? Not blood pressure, resistance. If you dilate the arterioles, the resistance will decrease. If you constrict the arterioles, the resistance will increase. Why? Because those small muscular arteries have the highest effect of on resistance among all our vessels. And this and if I want to add a point here, I would say most of the sympathetic control of the vessels is in the arterioles. Again, pours into the same bucket that I mentioned before. If the sympathetic system kicks in and constricts all the arterioles, the resistance will increase. Okay, I will be explaining in a bit the effects of increasing the resistance. I'm trying to build up here an image, inshallah. Blood pressure. The mean blood pressure will be highest in great arteries, and this makes sense because the great arteries are the aorta, and then say, for example, the femoral artery, they are receiving the blood sort of directly from the heart, and the blood pressure there will be the highest. The more you flow down, the less will be the blood pressure. As you can see here, it is decreasing. The more the blood flows in the circulation, the less the pressure will be. Okay. This is a quick summary right here. Couple of points to worth of mentioning in here. Look at, for example, the average blood pressure. طيب. Elastic arteries or the large arteries like the aorta, for example, has the highest blood pressure. Why? As I mentioned, because they are receiving the blood directly from the heart. Okay. And then the vena cava and the rest of the veins have the least average blood pressure when compared to the rest of the vessels. Okay. And then look at, for example, yeah, this is an interesting one. Look at the velocity of the blood flow compared to the diameter. Elastic arteries have very large diameter, like for example, the aorta. Okay, larger diameter, larger speed. Remember what I said? Larger diameter, larger speed, less cross-sectional area. Okay, look at the capillaries or the arterioles, the capillaries and the arterioles. Very high cross-sectional area, very low speed, smaller diameter. Hope it makes sense. If I want to go over the points that he mentioned here, the doctor, mean arterial pressure, which is this graph, is highest in the aorta and falls to low value and as much as 0 in the vena cava and the right atrium. I went over them all, by the way. Fine. Now I'm done explaining the parameters that affect the hemodynamics or the blood flow. And by the way, I forgot to mention this. If you have any question, feel free to interrupt me and just ask me immediately. But now onto the next concept, which is the transmural blood pressure. What does transmural blood pressure mean? Transmural is the pressure through the wall of the vessel. Okay, so if we want to calculate that math-wise, it's the pressure of the inside of the artery minus the pressure of the outside of the artery. So PI, P inside, PO, P outside. Okay. And this is basically the blood pressure that is measured with a blood pressure cuff. When we are measuring the blood pressure, we put a cuff on our arms. The blood pressure, this cuff or this machine is trying to measure this pressure. Okay. So I want you to think with me. If we have pressure inside the vessel, this means inside the vessel, the pressure inside the vessel is trying to push the walls apart, okay? And pressure outside the vessel is trying to compress the pressure of the wall. So it's like there are two opposite forces. One is pushing outside and trying to dilate the arteries, and one is pushing from the outside, trying to compress the artery. Okay. PI pressure is distending or stretching the vessel, and PO or the outside pressure is compressing the vessel. Okay. The difference is the difference of pressure across the blood vessel. Okay. And this is basically what influences the vessel diameter. And this is what we call dilate and constrict. Increases now think more with me. If we increase the pressure inside, which is pushing the wall, which is pushing against the wall, now we're increasing the tension on the wall, on the vessel wall, صح? That's why increased PI will increase wall pressure. Okay. At a constant vessel radius, the wall tension is exactly or exactly opposes the transmural wall pressure. What does that mean? So if the radius is constant, it's a hypothetical situation. If you have a tube, okay, and the radius of this tube will never change. طيب, the tension or the pressure pushing the walls against the walls and creating this tension will be opposite than the transmural pressure, which is the difference between the inside and the outside. Does it make sense? And this is basically called the Laplace's law. This scientist came up with this equation, which states that the wall tension equals the transmural blood pressure multiplied by the radius. Okay, so if we said that, if we hypothetically speaking, again, if we consider the radius to be constant, it will not change. This is not the case in our bodies, by the way. The radius is always changing, dilating and constricting. But let's say the radius will not change. So the wall tension is inversely proportional to the transmural wall pressure. This is what Laplace's law is trying to say, and this is basically what this point is trying to say. طيب. And again, here he's saying increased radius means increased wall tension. Why? Because when you increase the radius, this means the pressure inside is higher, pushing the walls apart, dilating it, creating more tension on the wall. Okay? Do you get it, or is there a confusion here? Look at the question here. Which vessel will have the greatest wall tension? I want someone to answer this. If you understand the concept here, you should answer this very easily, especially this concept. Which vessel will have the greatest wall tension? Yes, aorta, bravo. So why aorta? Because it has the largest radius. Larger radius means larger pressure inside, pushing against the wall, creating more tension. طيب, if you understood Laplace's law, aortic aneurysm, or the example of aortic aneurysm, should be easy. Well, let me explain what an aneurysm is, and then you should apply this Laplace's law on it. طيب. An aneurysm is simply dilation of the aorta. Yani this is the aorta, this is the thoracic aorta, this is the normal thoracic aorta, okay? Ascending, transverse, descending, and then thoracic aorta, and down there, the abdominal aorta. In an aortic aneurysm situation, you have dilation of a part of the aorta. So in this case, it's the thoracic aortic aneurysm. So the walls of the aorta are very weak, that because for any reason they are very weak, okay? When they are very weak, the very high or the blood coming from the heart with very high pressure will push against these walls, creating this dilation, okay, or creating these pockets in the aorta, okay, making it very, very weak and making it prone to rupture, okay, because the walls here are very weak and the pressure again is coming from the heart with the blood is coming from the heart with very, very high pressure, pushing against these walls, creating this pocket, and with time, this might rupture. طيب. How can we apply this to the Laplace's law we just learned? Again, basically, the first point, as we mentioned up, and the larger the radius is, the higher the tension. Number one, we are in the aorta, which has the highest tension among all vessels. That's one. Two, we have an aneurysm. And an aneurysm, mechanically speaking, an aneurysm is an increase in the radius of the vessel. So you have an increase in the radius. This means an increase in tension. صح? Increase in radius means increase in wall tension. Why? Again, because you have pressure inside pushing against the walls for creating more tension. Increased radius is increased tension. This is basically an aneurysm. Okay. And if we weight it a bit more, the pressure against the walls, the weak walls, let me say, will increase by time. Okay. The more the pressure is, the more the tension will be, ending up rupturing the wall. Okay. Oh, he's talking about how the surgery that treats the aneurysm, they basically go through, it's a procedure, it's not a surgery because it's a catheter through the femoral artery or the radial artery. So if you want to trace it back from the femoral artery all the way to the heart or to the place of the aneurysm, so radial artery, brachial artery, from the brachial artery to the subclavian artery, from the subclavian artery to the brachiocephalic, all the way to the thoracic aorta. Okay. They will go to the aneurysm location and put this piece of metal. It is called stent graft. This stent graft will bring back the environment or the environment of the aorta so that the blood can flow through it and these pockets will basically stay empty. It's called stent graft. Okay. Which decreases the pressure on the wall of the weakened artery or the aneurysm, and therefore decreases the wall tension so the aneurysm does not rupture. طيب, another point, driving pressure. What is driving pressure? If we want to talk about physics here, driving pressure is the pressure of one point subtracted by another point, whereas the second point is or one point is larger than the other. So it's the difference. So driving pressure is the difference between two pressures, 2 points with two different pressures. It's the difference between them. Okay, along the length of the vessel or a tube or whatever. طيب. And this is the reason why our blood flows down. Okay, I'll explain why now in a bit. Take, for example, the aorta. طيب. That's P1. And P2 or point 2 or pressure number 2, the right atrium. Why the right atrium? Because it's the starting point and the ending point of the blood. Think of it. Right atrium is, the aorta is the starting point of our blood. So blood comes fresh, pumped from the left ventricle to the aorta. That's point number. That's the first point of the blood. Okay, that's the first point of the blood into the systemic circulation. What's the last point? Right atrium. Because why? Because blood goes through the whole system, through the whole body, and through the vena cava, ends up in the right atrium. So the right atrium is the final point of the blood. Okay, that's for systemic circulation. Pulmonary circulation or circulatory system. What's the first point of the pulmonary circulation? It's the pulmonary artery. It's the first point where the blood arrives or it's a starting point for the blood in the pulmonary circulation. The pulmonary artery takes the blood from the right ventricle into the lungs. Okay, so that's the starting point. The final point or the ending point is the left atrium. Why? Because the pulmonary vein takes the fresh blood from the lungs and pumps it to the left atrium. So that's the final point. Okay, and if you understand the driving pressure, this is where they derive the MAP or the mean arterial pressure equation. So the mean arterial pressure is the diastolic pressure plus third or 1/3 of the systolic pressure minus the diastolic pressure. Okay, I'll explain this in a couple of slides, but this is a driving pressure, صح? Systolic P1 minus P2. This is a driving pressure. Okay, so we can say diastolic plus 1/3 the driving pressure. There's another derivative here. Let me show you. Let me explain. The pulse pressure. What is the pulse pressure and what is its relationship with the mean arterial pressure or the equation we just explained? Pulse pressure is basically the difference between the systemic pressure, the systolic pressure from the diastolic pressure. So the systolic pressure minus diastolic pressure. And this reminds us of this equation. So this is the pulse pressure, صح? Systolic pressure minus diastolic pressure. So this is the pulse pressure. So if we want to rephrase or rewrite the mean arterial pressure equation, mean arterial pressure equals the diastolic pressure plus third or 1/3 the pulse pressure, صح? Why is that? Because the systolic pressure is at 120 normally, and the diastolic pressure is at 80 normally, and the mean arterial pressure should be some in between or fluctuating between them. And the difference between them both is the pulse pressure. I hope you understand it. طيب, next point, systemic and pulmonary intravascular pressure. This whole slide is basically talking about a bunch of numbers here, or pressures of each circulation. By the way, you're supposed to memorize these. I remember we got a question about this. If I remember correctly, we got a question about this 2 years ago in our exam. The pressures outlined in the green are within the normal ranges. Okay, here he's talking about the difference pressure or the driving pressure of the systemic circulation. How do we calculate that? Again, the mean systemic arterial pressure minus the right atrial pressure. Why? Remember the driving pressure is P1 minus P2, صح? This is P1, this is P2. Let's start with the easy one, right atrial pressure. Right atrial pressure is P2. It's the endpoint, صح? Right atrium is the endpoint of the systemic circulation. And we cannot use aorta here, aortic pressure here, basically, because we are trying to find the systemic circulation's pressure. So we will take the mean systemic arterial pressure or the average systemic arterial pressure. Okay, we will use it to calculate the driving pressure of the systemic circulation. For the pulmonary circulation, it is the mean. It is the left atrial pressure, P1, P2. P2 is the left atrial pressure. Why? Because left atrial pressure is the end point or the final destination of the blood in the pulmonary circulation, and the mean pulmonary arterial pressure is again, we cannot take here the pulmonary artery because it's P1 and we want to calculate the pulmonary circulation's pressure, okay, not a specific point. So you will take the mean pulmonary arterial pressure or the average. Calculate it real quick here. It's 91 and 4. Okay? The doctor here is trying to say something, as a physician, it is important for you to know the normal ranges for blood pressures in different points in the body. Why? Rather than the actual number in millimeters of mercury. Because expected range as a healthy adult at rest will be able, if you know it, you will be able to calculate the driving pressure. And he's giving some examples here, but I explained it all up. Right. Different types of flow. We have two types of flow, basically, laminar flow and turbulent flow. What's the difference? Normal flow is the laminar flow. As you can see here by the figure or by the figure here, this is a normal vessel with a normal blood. The normal blood this is how the normal blood flows, okay, towards downwards or upwards, whatever, but in a laminar pattern. An organized fashion where the fastest flow is in the center of the vessel lumen, and the slowest flow is at the edge of the vessel due to friction. Turbulent flow is whenever the laminar flow is disrupted by any cause or by any reason. If we have narrowing in one point of the vessel, you will have turbulent flow. If you have a clot or you have any sort of something that's blocking right here, it will create another turbulent flow, and the blood flow will not be as organized. Okay, as the doctor mentions here, it greatly impedes the flow or disrupts the flow, and it increases the pressure, or it requires an increased pressure to maintain the flow. And this turbulent flow right here at this point will create a sound which can be heard by the stethoscope of a doctor, or as called as cardiac auscultation. Now we have a small equation right here which is called Reynolds number. What is Reynolds number? Reynolds number is basically Reynolds number is a measurement where that measures the how laminar the flow is, or if it's turbulent or not. طيب. Basically, the higher the number is, the more if Reynolds number is high, the flow is turbulent. If it's low, the flow is laminar. Okay, let me just make sure. Again, Reynolds number is a dimensionless index of the tendency of the flow to become turbulent. The higher the number is, the more likelihood of the flow to become turbulent. Right? The equation here, V is velocity, D is diameter. This is not a P. This I forgot what it is. A Greek letter, but I forgot the name of it, to be honest. But it stands for density. over, and this again is a Greek letter 2. It stands for viscosity. Right? You have to understand this here basically. The volume, or the velocity of the blood flow is directly proportional to Reynolds number. يعني if the blood velocity is high, there is a higher tendency for the blood to be turbulent, because higher volume means higher Reynolds number, and higher Reynolds number means high risk for the blood flow to be turbulent. Okay? If the diameter is wide, there is a higher tendency or a higher risk for the flow to be turbulent. If the density of the blood is more, okay, the Reynolds number will be higher, يعني more risk for the flow to be turbulent. طيب those three are directly proportional to Reynolds number. The denominator, which is the viscosity of the blood, is inversely proportional to Reynolds number. يعني and it stands for viscosity. If viscosity is higher, I'll explain what viscosity is in a bit. If viscosity is higher or larger, Reynolds number will be lesser, which means there is less risk of the flow to be turbulent, and it will be laminar. طيب. What is viscosity? Viscosity is how thick the blood is. It's not density, it's how thick the blood is. I want you to think of water and honey. So honey has a very high viscosity, water has a very low viscosity. You get me? So if the blood looks like honey, la samah Allah, it has very high viscosity. No, sorry. If the blood looks like honey, okay, or feels like honey, it has a very high viscosity. يعني the Reynolds number will be less. The flow will be laminar. Okay, and if the blood is like water, it's very, very thin and it's not heavy. It's just water. There will be turbulent flow. This is basically it. طيب, bulk flow law. Bulk flow law is basically, let me explain it. It's analogous to Ohm's law. What's Ohm's law? طيب. Let's read. The bulk flow law states that in a steady state, fluid flow between 2 points, fluid flowing between 2 points is equal to the difference in pressure between the same 2 points divided by the resistance to flow. And if we have flow, blood flowing, the difference between 2 points, the difference between the pressure of 2 points over the resistance will give us the flow. طيب. So if we want to, this is physics. Okay, let's take it and apply it to our bodies and to the cardiovascular system. So flow can be cardiac output, صح? Cardiac output is the amount of blood that the heart is pumping. Okay, so this is the blood flow. So CO, okay, or cardiac output equals P1 minus P2. Remember that P1 minus P2 is if I tell you P1 minus P2, what can you tell me from this? Basically, it's basically the driving pressure that I explained a couple of slides up. And we said that if P1 was the aortic pressure and P2 was the right atrial pressure, this is the mean arterial pressure or the mean systemic pressure. Why? Because or mean arterial pressure, sorry, not systemic pressure. Why? Because you got the very first point of the arterial circulation and the very last point of the, again, blood circulation, arterial circulation. So you end up with mean arterial pressure or MAP. Okay, so CO equals MAP or MAP. Am I right? Let me check. Yeah. So you get CO, okay, equals, I think I picked up figures, but I hope you're understanding it. MAP, okay, over resistance. What is resistance? It's TPR, صح? So right here we converted this equation this is annoying. All right, sorry. We converted this equation which is a physics equation, to a cardiovascular equation, basically. Cardiac output equals mean arterial pressure over TPR. And this equation right here, if we rearranged it, we will have this, which is mean arterial pressure equals cardiac output, mean arterial pressure equals cardiac output multiplied by TPR, okay? This is used for systemic circulation. And this is a very, 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 very crucial and very important equation to be used throughout your studying cardiology, okay? First year, third year, whenever, because the whole circulation or the whole blood flow hemodynamics depends on it. So if you increase, if you decrease the resistance, you will increase the cardiac output. And you start changing between those parameters, and you will get different. Every time you change a value, you will get a different parameter or a different value. And rearrange it again for TPR, you will get this. In TPR, if we increase cardiac output, we will decrease the TPR, and so on. So that's why it's very important. And many things later on, inshallah, will depend on it. Let me close this because it's annoying. Fine. And he right here is explaining whatever I said. Another equation is this. It's quite similar to it. Let's read. We know what determines CO or cardiac output, which is heart rate and stroke volume. You know the equation. Cardiac output equals heart rate multiplied by stroke volume. But what determines TPR? Okay, and in this equation, cardiac output, we know what determines cardiac output. Disregard this equation. We know cardiac output is determined by either heart rate or stroke volume. If you increase heart rate, you will increase cardiac output. And if you increase stroke volume, which is the contractility and how much you eject blood in a minute, you will increase cardiac output too. But what increases TPR? Okay, let's see. The properties that determine resistance to fluid flow were by the physician Jean Poissy or Poiseuille, and he created this law, this equation right here. Let's explain it. He established that resistance to steady flow along a straight cylindrical tube or a vessel, for example, is proportional to the tube length and fluid viscosity, which is this, okay? And inversely proportional to the tube radius raised to the power of 4. I hope it's written somewhere. It's not written anywhere. This is the resistance, okay? Always capital R is resistance and a small r is radius. Okay, don't be confused. The equation basically says resistance equals 8 multiplied by L is the length of the vessel, okay? And this, it's not showing here because the doctor used the Greek letter that stands for viscosity, inversely proportional to the radius, okay? And this is supposed to be viscosity too, by the way. Yeah, so if you increase the length of the volume, if you increase the length of the vessel, resistance should increase. If you increase the radius of the vessel, increase the radius, yani constrict, resistance should decrease. Yeah, sorry, you see, I confused you. If you increase the radius of the vessel, yani dilate, you should decrease the resistance. Why? Because both of them are inversely proportional. You increase one, you decrease the other. And the ones in the numerator are directly proportional. How can we apply that? If we combine the Poiseuille's law and with the bulk flow law, which we converted to make it as cardiac output equals mean arterial pressure over TPR, or the resistance, we combine them this way, okay? What can we get? We can see from this that flow is extremely sensitive to the vessel radius. Flow, which is also cardiac output, again, according to this equation, is very, very, very sensitive to the radius. And if you change the radius by one, let's read here. A fall in radius from 1 centimeter, which is, for example, in the aorta, to 0.01 centimeter in the arteriole, will increase the resistance by a factor of 10 to the power of 8. If you solve this equation, if you try to solve this equation, and you used some numbers, right? You used numbers here and instead of these letters, and the numbers denoted that there is a fall in the radius, from 1 to 0.01. The resistance will change by a factor of 10 to the power of 8. This is very important, and this is why is this very important, because it explains why the arterioles are the main site of resistance in the circulation. Because basically the drop of, or the rate, the size of the radius drops from the aorta to the arteriole, and the biggest to the smallest. You get me? That's why the arterioles are the main site of resistance in circulation. Again, because as you can see here, a small change in the radius is enough to make a huge difference in the resistance. Okay, hence why the most effective way to control the resistance is to regulate the radius of systemic arterioles via vasoconstriction and vasodilation. Yep. A quick summary here, basically. This equation is the same equation as cardiac outflow equals the difference or the driving pressure P1 minus P2 over the resistance, which is mean arterial pressure over TPR. Gives us this nice equation, this very, very important equation that you will be using every time you study cardiovascular system. Okay. Again, here the doctor tries to apply it to the pulmonary vascular resistance. And in the pulmonary circulation, the pulmonary vascular resistance equals, he's trying using this equation. Let me show you. Okay, he did not mention it here, but you can rearrange this equation to, I'm not going to write again because it's short. You can rearrange this equation for TPR. It will be TPR equals mean arterial pressure over cardiac output. Okay, so if we want to calculate the pulmonary vascular resistance, we will have PVR equals the mean pulmonary artery pressure in PAP minus the pulmonary wedge pressure, because you have, I'll explain now why, over CO, over cardiac output. So you replace mean arterial pressure by mean pulmonary artery pressure in PAP minus pulmonary wedge pressure, and why to find the pulmonary the pulmonary vascular resistance PVR or instead of TPR. But why did we subtract here? Because you basically want to find the driving pressure or the difference pressure instead of one pressure, which is the mean arterial pressure. And remember, TPR is SVR, total pulmonary pressure, total peripheral resistance, sorry, and SVR is systemic vascular resistance. By the way, they will be more explained in hemodynamics too by my colleague somehow. Fine. Again, to the series arrangement and parallel arrangement. Now you should understand them well after all of this explanation. Let's go over them really quick. And he adds another point here. If you want to, before this, remember, series arrangement is series circulation is the systemic circulation in all, or the pulmonary circulation. Yani, the circulation from the heart to the organs or the systems. One of them is the lungs. Okay. And if you want to calculate the total resistance, you will have to add every resistance. So R1 plus R2 plus R3. You can do this because it is a series. Okay. In a series, you can add 1, 2, 3, 4, 5 to find the total. Okay. I know this sounds simple, but when I explain the parallel, you understand what I mean. And you can see here, R1 is the artery, R2 are the arterioles, R3 are the capillaries, and each one of them is going to a set of, let me say, an organ or a system in total. Okay. And if you drop one of them, if you remove one of them, the whole series will be disrupted. Kind of like physics, I'm not joking. Okay. When vessels are arranged in series, the total resistance is calculated by this equation. Right? However, in a parallel, the case is different. You cannot just calculate R1 plus R2 plus R3 plus R4 to get the total resistance in a parallel circulation. You have to add a 1 over. So 1 over the total resistance, or 1 over parallel resistance 1 plus 1 over resistance 2 and so on equals 1 over the total resistance. And if you want to find the total resistance of a parallel circulation, you have to get rid of this 1 over. Okay, I'll show you how. And why is this important before explaining the math of it? It's because now the total resistance of the parallel system is less than the lowest individual vessel resistance. Okay, and this explains why the resistance, or this explains why if you change the resistance in one of the capillaries, you want to change the whole resistance of the capillary system. Okay, it's written here: the resistance of arterioles in one organ can be changed without significantly altering the total resistance of the vasculature. Okay, again, remember that organs have parallel within the organs or within the system, you have parallel circulation. So if you change the resistance of one of the arterioles in this organ for any reason, you will not do a huge change in the total resistance of this vasculature. Okay. How does this help us? It permits the redistribution of blood flow in instances or examples like exercising and so on. Another point, another important point and advantage, the total resistance of the parallel system, again, this, it's less than the lowest vessel resistance. And this explains why the capillary system provides such a low resistance. Despite the fact that each capillary have very high resistance, each capillary have very, very high resistance. R1 has a very high resistance, R2 has a very high resistance, R3 has a very high resistance. Each one of them is a capillary, okay? But because you're adding 1 over this resistance plus 1 over this resistance, this very high resistance, plus 1 over this very high resistance, and you're ending up with 1 over the total of all of these, okay? This is why each very high resistance, or the addition of all of these very high resistances will end up with a very low resistance, okay? And this explains the capillaries and the arterioles system. Now, if you want to find the total resistance of a parallel, and I think this will be a question in the exam, all you have to do is, I'll show you in this practice question. So without seeing the answer here, so if we have this diagram that represents a capillary bed, okay? Each vessel has a resistance of from R1 to R5. The R1 and R5 are in series, as you can see here. 1 is a series and 5 is a series, but R2 to 4 are in parallel. What is the total resistance? So if you want to find the total resistance of these, we need to find first of all the total resistance of these, صح? Because these are in parallel. It's different than series. You can't just add them all together. What are we going to do? We will have 1 over R2 plus 1 over R3 plus 1 over R4 will equal 1 over R total, صح? And 1 over 18 plus 1 over 18 plus 1 over 18 equals some number. Here he did some other calculation, which is easier, honestly. If you have, I think I have to write here. If you have, let me try to explain it without writing. If you have 1 over, okay, here. If you have this equation, but you need to find the R total, what do? You basically, you literally just make all of the, you put 1 over all of these, okay? You have R total. So R total is all of these as a denominator and the numerator is 1. And this is what he's doing here, basically. So ML, the resistance from point B to C, which is R2, 3, and 4, is equals 1 over 18 plus 1 over 18 plus 1 over 18. Did you get it? So this is the parallel, this is this resistance, and this is the R3, and this is R4. Right? R1 over R4, 1 over R2, 1 over R3. And all of them, 1 over all of them, will give you the total resistance of this parallel system, parallel circulation. So he solved for it and he got 6. Right? Now he found the total of this. He just has to add 1 with this with 2. صح? Resistance, and this is what he did: 1 plus 6 plus 2. He ended up with 9. So the total resistance of this capillary bed is 9. صح? What is the? He did not mention the. In resistance you don't have. In resistance you don't have a unit. Sorry, forgot that. But he also asked for what is the flow through this capillary bed. if you want to find the flow or the cardiac, or which stands for cardiac output again in a larger setting, but in this, it's just the flow. You need to find the driving pressure, which is P1, P2, 90 minus 0 equals 90, okay? And this is the driving pressure. And the equation is flow equals driving pressure over resistance. Do you remember this equation? So driving pressure is 90, or 90 minus 0, over resistance, which is 9. This is 10. So 10 volumes per unit time. And there is a quick video here explaining how you solve it if you want to watch it. Now, we're done with the whole lecture. 2 more slides. He's trying to tell you how can we measure the cardiac output. This machine is called an echocardiograph. Echocardiograph basically shows you the heart and the chambers of the heart, the valves of the heart, and in some way you can calculate the cardiac output using Doppler flow probe, which basically colors the blood being ejected from every chamber through every valve to the aorta. There's a nice video here explaining it. You don't need to know more than that. What are other ways we can measure the cardiac output to the fixed principle PA? I will explain it now. Next slide. Pulmonary artery catheterization, most widely used. Echocardiography, I just explained it. You only need to know these. Like, what is a fixed principle? Fixed principle basically says, if you can know the amount of blood or amount of oxygen the blood is taking from the lung and the amount of oxygen being used in the whole body, this blood is the cardiac output. So they came, or this scientist, which his last name is Fick, came up with this equation, which says VO2, or the volume of the oxygen in your lung, or you're breathing in, or in your lung, this is your lung, this is your vessel, over the difference between CA. CA is the oxygen content of the blood in the peripheral arteries, such as the radial artery or the pulmonary vein. Remember, the pulmonary vein carries oxygenated blood, صح? Minus CV. What is CV? CV is basically oxygen content of mixed venous blood, such as the pulmonary artery. Remember, the pulmonary artery is or carries deoxygenated blood. طيب? So equals the cardiac output. Basically, CA minus CV is oxygen in arterial blood minus oxygen in a venous blood or mixed venous blood. And here he says a very important note, the mixed venous blood is only found in the right atrium, right ventricle, and pulmonary artery, because these are the final destinations of the deoxygenated blood. Basically, this is how you can find cardiac output. This is the last slide. A practice question. He's trying to, it's just a question that gives you the VO2. It gives you the VO2 and gives you CA and CV and tells you to find the cardiac output. What are the numbers here? Okay. This is the explanation. So VO2 is 250 over 0.20 minus 0.15. So 0.20 is the arterial blood, and 0.15 is the venous blood. Sorry. 0.20 is the oxygen in the arterial blood, and 0.15 is the oxygen in the venous blood or the mixed venous blood. You do this equation, you will end up with 5 liter, which is the normal cardiac output in a normal healthy person. This is it. Please give me your feedback, and if you have any question, now is the right time to ask. If you don't have any question, please scan this QR code to give me the feedback, and we should be done. No problem. Thank you, Saad, for being interactive with me.